take up the subject of generation of FM signals today, but before I do that, let me quickly review what we did in the previous class. We looked at the bandwidth of FM signals, right, and one of the important results that we derived was that the bandwidth of an angle modulated signal is given by the so called Carson's formula, which for the case of a pure sinusoidal signal looks something like this, where f sub m is the frequency of the sinusoid, beta is the modulation index, and this is the case for wideband FM. And if you remember how we derived this formula, we basically obtained a power series, a series expansion of the FM signal, not the power series expansion, but a series expansion of the FM signal in terms of in terms of the various frequency components present in the signal, by making use of a Fourier series expansion of the complex envelope of the FM signal, right? The complex envelope being e to the power j beta sin omega mt, right, and that is a periodic signal. So, we could obtain a Fourier series which we could use to obtain a series expansion of the FM signal itself, right. Equivalently, we also discussed, this was just a matter of discussion, we did not derive this, for the general case when the input signal, the modulating signal is not a sinusoid, when it is a general signal, message signal m of t, then the bandwidth formula is more or less the same, except that this beta gets replaced with a factor d, and f sub m gets replaced with w, right, where d we call the deviation ratio, right, and it is defined as delta f by w. Remember, beta could also be interpreted as delta f by fm, right. So, there is a direct analogy. So, by making use of that analogy, and of course, this is based on empirical and theoretical calculations, right, and these rules for calculating the bandwidth of an FM signal are called Carson's rules. Carson's rules, and these are the results for the case of wideband FM, right. For narrowband FM, what is the case for narrowband FM? And beta is very small, or in other words, the deviation ratio is much less than 1. So, either when beta is much less than 1 or d is much less than 1, the kind of FM that we work with is narrowband FM, right, and for this case the bandwidth is essentially, this becomes a negligible part of the total bandwidth, and essentially it is either 2 FM or 2 W, precisely the way we had the bandwidth in the case of AM signals, right. So, this is a review of the bandwidth of FM signals, angle modulated signals, and we now quickly review what we discussed so far about generating FM signals. As I mentioned, for FM generation we have two class of methods. The so called direct methods and the other ones, for the same reason, because they are not direct in this sense, are called indirect methods of FM generation. Basically, direct methods use the concept of a voltage controlled oscillator, right. So, let us talk about direct methods first. That is the expansion for VCO, a voltage controlled oscillator. Now, what is the idea of a voltage controlled oscillator? You have to devise a variable frequency oscillator, right. You can devise a variable frequency oscillator in which the frequency can be adjusted by tuning the oscillation frequency, right. And as if you have some idea of oscillators, you may also know that the oscillation frequency of an oscillator really depends on the tuned circuit present there, right. So, and I do not know whether you know something about oscillators already. In case you do not know, it is basically a feedback amplifier, right. An oscillator is essentially a feedback amplifier, just to remind you if you do not know, in which the feedback is not a negative feedback, but a positive feedback, but the positive feedback occurs at a certain frequency, right. You reinforce the positive feedback to happen at a certain frequency, right, and therefore the oscillating frequency will really depend on what is that frequency at which the positive feedback happens, and typically that is determined by the resonant frequency of some tuned circuit, right, which is present in the circuit. We will look at some detail of that a little later. So, basically that is how any oscillator works, but that is not a voltage controlled oscillator, that is an autonomous oscillator. You supply the power to the oscillator, and in a few nanoseconds or microseconds it will start to oscillate at the frequency of interest, right, depending on the kind of frequencies you are working with or kind of circuits you have. A voltage controlled oscillator on the other hand is one where this frequency at which feedback occurs, right, can be controlled by an externally applied voltage, right. So, somehow you have to make in this kind of a system the tuned frequency or the resonant frequency depend on some voltage, right. Now, how to do that is something we will discuss later, but that is the idea. If you can do that, then you have what is called a voltage controlled oscillator, and if you have a voltage controlled oscillator of this kind, your modulating signal can serve as the controlling voltage, right. So, if your controlling voltage happens to be the modulating signal, the oscillation frequency will now depend on the instantaneous amplitude of the modulating signal, right. So, basically that is the idea of a voltage controlled oscillator in a nutshell, but I will discuss in some more detail a little later and come back to it. But this is one kind of a voltage oscillator, that is one based on let us say using a resonant frequency which is made somehow proportional to the applied voltage, right. There are other kinds of voltage control oscillators as well, right. These are called relaxation oscillators. Or in digital electronics terms, they are more commonly known by the name of astable multivibrators. In this kind of circuits, there is no resonant circuit, there is no LC circuit in this, right. It is basically based on the operation of a pair of transistors switching between on and off states, right, and through appropriate feedback a pair of transistors alternately switch on and off. At one time one switch is one transistor is on, the other is off, and then the role gets exchanged with each other, and this happens through a feedback mechanism between the two circuits, between the two transistors, right. So, these kinds of oscillators are called relaxation oscillators, and they do not use a resonant circuit. There is a reactive component in the circuit, there is a capacitance of some kind, there is a resistance, but there is no resonance effect that is used here, right. So, these are known by the name of astable multivibrators. Basically transistors are used as switches. You know that transistors can be used as switches, and the switches go on and off alternately, right, and because they go on and off alternately you can tap off the voltage of any particular transistor, and that gives you a square wave oscillation. So, the output waveform of a relaxation oscillator, unlike that of a resonant frequency oscillator, is a square wave. For a resonant frequency oscillator, the output is a sine wave, right, because there is a resonant frequency and the system oscillates at that resonant frequency, it produces a sine wave of that frequency. In a relaxation oscillator, the system produces a square wave, because it is based on the phenomenon of switching on and off of transistors, and therefore you get a square wave at the output rather than a sine wave. So, this is in a nutshell. We shall discuss this in some more detail. This is something that you will learn in some other course, like a course in digital electronics, if you have not already done so. So, but then there are various kinds of oscillators of the first kind also. For example, I mentioned the name of klystron, right, which itself acts like a voltage control oscillator for a certain range of frequencies, right. But then to how that works requires you to understand how what is a klystron and how it works, which is outside our scope at the moment. So, at an appropriate time and in an appropriate course, you will learn about klystrons and magnetrons, and probably a course on microwave devices. Now, as against this, we can have indirect methods of generation, and let me discuss that first. But before coming to that, let me also review one more point that I made, that if you have a system for generating FM signals, let us say a voltage controlled oscillator, right, you could use this to generate both AM as well as both FM as well as PM, right. For FM generation, the controlling voltage will be directly the signal MT itself, right. However, for generating a PM signal, you will have to have a differentiator, right. So, you maybe I can put a switch here. So, if this switch is on, this signal here x of t would be an FM signal. If this switch is on, this will be a phase modulated signal, right. So, if you have a voltage controlled oscillator of any kind, you can make it work either as a phase modulator or as a frequency modulator, right. That is something that we have discussed already. So, let us discuss the indirect method in some detail first. Okay. What is the basis of an indirect method? It is actually a two-step process. In the first step of an indirect method, so it is a two-step process, you generate a narrowband FM signal. Now, why do we want to do that? Because we know that in some sense a narrowband FM signal has a spectrum very similar to that of an AM signal, right. Now, that fact can be made use of to generate a narrowband FM signal. To be more explicit, let us look at the FM signal or angle modulated signal. This is a general form of the angle modulated signal. If you choose this function phi of t as proportional to MT, you get phase modulation. If you choose it proportional to the integral of MT, you get frequency modulation, right. That is what you have. So, you have some function of phase function, which is a function of time, which is controlled by your modulating signal m of t, right. Let us expand this simple trigonometry. A cosine omega c t into cosine of phi of t minus a sine omega c t sine of phi of t. Now, for narrowband FM or narrowband angle modulation, what can we say about this phi of t? Is there any property that you can ascribe to phi of t when the angle modulation that we are generating or that we have is narrowband in nature? What was the condition for a narrowband? That beta is small, right? Beta is much smaller than unity. What does it imply on the nature of phi t itself? Phi t itself will be small, right? So, because this, let us say if it is PM, this will be beta sine omega beta cosine omega mt, right. So, if beta is very small, the amplitude of this phase would be very small. So, the largest magnitude of phi t would be very small. Similarly, when it is Fm, the same thing will still happen, right, because all that happens is it is suppose mt is cosine omega mt, this becomes sine omega mt, right, and beta is small, you have the same problem. So, when phi of t is very small, you can use the approximation that cos of phi of t is nearly 1, right, and sine of phi t is phi t, right. So, you are left with a cosine omega c t, this is approximately of course, minus a times phi of t into sine omega c t, right. So, using the small angle approximation, and that approximation is valid because we are assuming here that this is a narrow band signal, right. Okay. Now, suppose you were to generate this signal, can you tell me how to generate this? This is just the carrier itself, to which you are adding what? A DSBSC signal, right. Here sine omega c t is a quadrature carrier, right, and phi of t is your, you can think of that as a modulating signal. In fact, phi of t is going to be k sub f times integral of mt or k sub p times mt, right. You have access to both of them. So, by using an appropriate form of phi of t, you can realize the second term of this equation by a DSBSC modulator. So, I do not have to have any voltage controlled oscillator, any stable multivibrator, all I have to do is use the good old DSBSC modulator by as a multiplier and generate this signal, and this would be a narrow band FM signal, right. What is the difference between this signal and the normal AM signal? In the normal AM signal, both this term as well as this term are they are carriers of the same phase. Here the two carriers are in quadrature. That is an important difference. I mean, that is, although they have the same spectral components, one of the questions that should have bothered you, I do not know whether you thought about it. If two signals have the same spectrum, normally you would like to think that they would be the same signals, because spectra and time domain descriptions are equivalent, right, one implies the other. So, actually they are not identical in that sense, there is a difference. If they were exactly identical, the spectral components are the same in terms of magnitude, but there is a difference in detail, and that is a difference in detail, right. It looks like here the carrier part and the modulated carrier part, they are in phase quadrature, right. So, although the basic frequency components remain the same, their relative phase relationships are different. That is something I have already discussed, right. That is, the phase gets reversed in the case of the FM signal, right. Okay. So, realization of this signal, let us say if you are generating FM, you start with m of t, then because in FM the phi of t will be proportional to the integral of mt. So, you will have an integrator here. Integration is very easy to do. Differentiation, integration are things you can easily do using circuits, right. I am sure you already know that, right. For example, can you tell me how you can realize approximately an integrator by simply RC elements? A simple resistance followed by a simple resistance in series followed by a capacitor in shunt, right, or you could use an operational amplifier to give you a more precise integration operation, right. So, integration is something that you can do in a very straightforward manner. This is followed by a DSBSC modulator, in which the carrier is 90-degree phase shifted version of the signal, the carrier that you start with. So, you have started with let us say you have an oscillator which produces a cosine omega ct, right. You phase shift it with 90 degrees, and these two things are then added or subtracted, whatever subtracted in this case, and that produces your narrow band FM signal, right, because this will give you A of phi of t sin omega ct. This is A cosine omega ct, and that's how it is. Yes, Chiritan.
I started off taking an FM signal where I had a constant amplitude.
Yes.
So now I am getting the signal A cos omega ct minus A phi t.
Very good question, because the question is, will this signal be of a constant amplitude? That is the question, right? We start the question. Let me repeat the question. This is supposed to be a constant amplitude signal, right? Whereas it appears that I am now generating this signal by an amplitude modulation process. So there seems to be some fallacy somewhere in terms of the fact that you started with a constant amplitude signal, but you are using an amplitude modulation process to generate it. Well, the answer is indeed yes, there is a problem. You may not remember, this is an approximation, right? You have to remember the fact that this is an approximation. This is not the exact signal that you really want, right? But to the extent that this approximation is valid, this signal will turn out to be approximately of constant amplitude, right? Is that okay? So to the extent that this approximation is valid, so this, therefore what is the circumstances under which it is valid? Phi of t should be much less than 1. As long as that condition is satisfied, this signal will tend to have a nearly constant, I am not saying constant, I am saying nearly constant amplitude, right? There could be some amplitude variations of very small magnitude. Not equal to 1, much less than 1, because that is the condition under which I have derived this equation. Phi of t should be much less than 1, so that cosine of phi t is approximately 1 and sine of phi t is approximately phi of t. So the condition is,
so why only 1? Shouldn't it be close to 0?
well, that is what it means. If I say phi of t is much less than 1, basically you are saying it is very small, right? That is basically what I am saying. That is right. That is the other difference that I discussed. That is, the upper sideband and the lower sideband carriers are phase reversed with respect to each other. And the other thing is, if you look at it in the time domain, if you think of it as consisting of quadrature carriers, the two carriers are basically in quadrature. They are, unlike an AM signal, these two terms have the same phase, whereas here the two terms are quadrature. That's all. So that's a different. The earlier difference was told in the frequency domain. This is the difference in the time domain.
This is like that will be opposite sign.
Yes, you can check that out. Okay. All right. So I hope these questions are answered. The question was about the amplitude variations. So it is, I hope, clear that amplitude variations, to the extent our assumption is valid that phi of t is much less than 1, would not be there, right? Or would be would be present in very small magnitude. There could be some amplitude variations, and that is a possible problem that you have to keep in mind when you are dealing with narrowband FM signals, right? So let me emphasize again. Actually, more precise way of saying it is, let's put it like this, that phi of t is much less than 2 pi. I think that's a more precise way of stating the condition, because that is a condition under which cosine phi t can be approximately mentioned to be phi of t and sin phi t as approximately equal to phi of t. So really speaking, this is the condition we are talking about, and this is the narrow band approximation. So if this approximation is indeed valid, you will have to make it valid if you want to use this method to generate the FM signal. Therefore, what you will get at the output is not a wideband FM signal, but a narrowband FM signal. You have to keep that in mind. That is why I said it is a two-step process. In the first step, we generate a narrowband FM signal, and in the second step, I convert this narrowband FM signal into a wideband FM signal. Okay, so that is step 2. convert narrowband FM that we have generated so far to wideband FM. Okay. There is some talking going on here. If you remember, I discussed not to do that because it gets picked up and disturbs us also. If you have a question, please raise the question, but don't talk. How do we convert the narrowband FM signal into a wideband FM signal? Any suggestions? What should we do? What is our, let's go back to our definition. This is the FM signal, right? The assumption that we made was that this is very small. So we have to get rid of that assumption that it is very small, right? We have to allow phi of t to take large values. We are starting with phi of t with small values. How can I make it large values? Having got the signal, what I have with me at the input is this signal that I have generated, right? This signal. This is what I have generated, right? Which is equivalent to this signal, but phi of t being very small. How do I convert this into one with large variations rather than small variations? Any suggestions? Multiplying what?
Multiplying the cosine.
Somehow we have to multiply the argument of the cosine function. That is important, not the cosine function itself. We have to multiply the argument of the cosine function. Of course, in the process that will also modify your carrier frequency, right? So if you have a method of multiplying the argument of your cosine function that you have generated, right, you would achieve frequency, you would achieve wideband FM, right? And this is done through a process called frequency multiplication.
So one thing was that if we multiply it with some cos pi 2t, and then we'll get some omega ct plus phi 1 plus phi 2t, which is sufficiently large that we want. Where phi 2t is also proportional to empty or integral of empty. Is it possible?
It is not relevant to as a method for generating FM signals. Right? Let's discuss that in the tutorials. Okay. So that step of converting a narrowband FM into wideband FM has to be carried out by what is called, so this is step 2, the frequency multiplier. A frequency multiplier precisely does the operation that I just mentioned. That is, it multiplies the argument of a sinusoidal or sinusoidal function by a certain factor, right? Now again, there are several ways of realizing a frequency multiplier. I will discuss one of them at the moment, which you are familiar with already. Maybe not by this name, but something that we have used already in the context of generating AM signals. And this is based on the principle of using a nonlinear device, right? So you have what is called an nth law device. By an nth law device, I mean a physical device which produces an output which is the nth power of the input, right? So let's say your narrowband FM is the input to this signal, input to this device. Let's call this E sub IT, right? And so E sub IT here is A cosine omega ct, and for simplicity of discussion, let me make this beta sine omega mt. All right. I'm taking this to be an FM signal with the modulation index beta, right? When the modulating signal is cosine omega mt, then the output of this device would be the nth power of this. That means it will be cosine to the power n, and you can use the now trigonometric identities, and you know that when you make use of those trigonometric identities, among other terms you will get one term corresponding to n times this argument, right? Which essentially means you will multiply this argument by a factor of n that you are looking for. To remove other terms, what you have to do is have a band pass filter which is tuned to n omega c, right. So, that is the second stage of this multiplier. You have a band pass filter with a center frequency which is equal to n times f sub c. So, that will produce an output E sub 0 t or E sub o t, which is some a prime cosine of n omega c t plus n beta sin omega m t, right, and that increases your modulation factor by a factor of n. Okay. That is the principle. So, if you have a square law device, you will get n equal to 2. If you have a cubic law device, you have n equal to 3, and so on and so forth, right. Usually these multipliers, frequency multipliers, are realized as either frequency doublers or frequency triplers, right. When n is equal to 2, you have a frequency doubler. When n is equal to 3, you have frequency triplet, because typical nonlinearities, typical nth law devices have powers associated with them of 2 or 3, right. The nonlinearities that you typically get from physical components like junction diodes or p-n junction transistors is of the order of 2 or 3, right, in which case you can typically build frequency doublers and frequency triplers, right. But it does not mean that you can only do multiplication by a factor of 2 or 3, because I can put several such frequency multipliers in cascade, right, and typically there will be a cascade of frequency doublers and frequency triplers, right, but I can use any number of them to multiply this argument by any integer n that I wish to generate, all right. So, of course, in the process you have modified your carrier frequency to n omega c, which is something that which is actually useful. Why it is useful? Because typically, the carrier frequency that I have used at the in the generation of narrowband FM signal becomes much smaller, and I need to build a balanced modulator. You remember that the DSP-SC modulator is essentially a balanced modulator at a much lower frequency. It is much easier to realize a balanced modulator at a lower frequency than at a higher frequency, because of problems of leakage and things like that, right. So, balanced modulator is much easier to build at a lower frequency. So, I initially start with a lower carrier frequency suitably, so that I have the required carrier frequency after multiplication. Sometimes I may have to do additional manipulation to make sure that I get the carrier frequency that I want and I get the modulation index that I want, because they can contradict each other, right. So, we will look at that. In fact, let us look at this in slightly more detail now. This is the principle, but the details can be a little more involved. This method of realizing a frequency modulator using the indirect method, that is, was due to a gentleman called Armstrong, not Neil Armstrong. You are familiar with Neil Armstrong? Right. This is a more historical name, in the sense it is older. He was a pioneer in this whole business of making FM popular, right. In fact, I think the entire credit for the commercial application of the frequency modulation should go to Armstrong. He did absolutely pioneering work in this area. It is another matter that he died as a failed man, because during his lifetime he could not achieve this purpose, right. He kept on telling people and demonstrating by experimental setting up of such stations that FM is far superior to AM in various ways. We have not discussed that yet, but we will discuss it later. and but people refused to believe him basically for commercial reasons, because there were a lot of vested interest which didn't want to change the existing AM stations, right. So he died as a failed man, but later it picked up in his name, of course, and everything worked very well. Anyway, that is just part of the sidelight which I wanted to just mention, because some of these things also you should know the history behind how these things were done. People just didn't think of them overnight and they started to work. A lot of great effort went into bringing about these concepts, not only on paper but also realizing them as equipments, as systems which will be deployed in practice, right. And a lot of hard work goes into that, right, which is invisible in a textbook, right, but which is very much part of the story, which you should know, right. So I'd like you to read more about Armstrong if you can. It's a very interesting story and a slightly tragic one. Okay. Now when we talk about this commercial exploitation of FM method, this FM method, which is based on Armstrong, this idea converting a narrowband FM signal to a wideband FM signal, which was basically due to Armstrong. So let's look at a commercial FM transmitter. Okay, so to start the discussion, let us say we fix a requirement, and that will also give us some idea as to what are the typical values that we use in commercial FM transmission. Let us say we want a carrier frequency of 91.2 megahertz. What is our FM band here? That is only one frequency.
88 to 108.
88 to 108. Good, at least somebody remembers that. So it lies in that band, right. And typical frequency deviations that you are looking for in an FM signal which is commercially being used for broadcast purposes is of the order of 75 kilohertz. It is more or less a standard value, right. That is the kind of frequency deviation you are looking for, and this will correspond to wideband FM, because as you can see is how do you decide whether the frequency deviation that you have corresponds to narrowband or wideband FM? You should compare it with the highest frequency component present in your modulating signal. Remember that, because your how is beta defined? Delta F by FM. And how is D defined? Delta F by W. W is the bandwidth of your modulating signal. Suppose your modulating signal is let us say voice speech signal, right, or let us say we are talking of music, right. What is the value that you will have for W? It is about 10 kilohertz, 15 kilohertz, of that order, right. So therefore the ratio would be of the order of 5 or more, right. So it is definitely not narrowband FM, because for that the ratio should be much smaller than unity, right. So therefore this is wideband FM we are talking about. So how do we generate this combination? That is the issue. So if you want to generate using the indirect method, in the beginning I can't generate delta F equal to 75 kilohertz, it is clear. I must choose a value of delta F 1 which produces a beta which is much less than 1, right. And let us say our FM, the modulating signal that we have will be typically speech, audio and music, right, those kinds of things. The typical spectra of these would range from 50 hertz at the lower end to about 15 kilohertz at the higher end, right. So keeping that in mind, can you recommend a value of delta F1, that is in the first stage when I generate the narrowband signal, what should be the corresponding frequency deviation, keeping this data in mind? It should be such that this upon the highest frequency component that you have is much less than 1, right. Basically, okay, you have to define what is much less than 1. Now, sorry, it should not be just the highest frequency component. That is a slight mistake in what I said. You have to make sure that over all the frequency components that you have in the signal, at no frequency is beta less much this condition is satisfied at all those frequencies. So, in which case which frequency is more important, this one or this one? It is the 50 hertz which is more important, right. I made a small mistake earlier in making my statement. So, you have to make sure that at 50 hertz the ratio of delta f1 to fm is at least is not close to 1, right. Now, in order to avoid too many problems later, let us accept that a value of value of 0.5 will be acceptable. So, in which case I can choose delta f1 as 25 hertz, right. This will produce beta equal to 0.5, right. It is not exactly much less than 1, but it is still okay, right. The smaller you make it, what are the pros and cons? The smaller you make it, the better your approximation, but there is another implication also. That means you require to have a larger frequency multiplication factor later, right. So, you have to choose some compromise value suitably. So, having decided that, so we already know how to realize the narrowband FM generator now, because we have given all the parameters, right, that we need. So, how do we get delta f equal to 75 kilohertz now? I need a multiplication factor n which will be 75,000 upon what was delta f1? 25 hertz, right, which is 3000. I need a frequency multiplication factor of 3000 to get my required frequency deviation, peak frequency deviation. Is that clear? We are going through a design process here, right. We will look at the final picture after the design process is complete. So, this is fine, this is not an issue. We can always realize any frequency multiplication factor by using a cascade of frequency doublers and triplers. Typically what you will do is, because you know that you can realize this n in terms of powers of 2 and powers of 3. So, it is best to express this n in terms of a closest factor set of factors which will enable us to realize this factor in terms of doublers and triplers, right. For example, this is approximately equal to 64 into 48, that is really about 3072 rather than exactly 3000. Design process always you do these approximations, right. So, if you choose these factors 64 and 48, your actual value of n will turn out to be 3072 rather than the 3000 that you exactly want, right, which is okay. That will give you a slightly larger peak frequency deviation, right. So, you require a 6 frequency doublers, right, and you require how many? Again here also you can write 4 doublers here, 1 and 1 tripler, right. So, total of 10 doublers and 1 tripler, right. So far so good, there is no major problem here, but there is a problem. If you multiply, let us say, okay, we did not talk about FC1, right. Now, typically as I said, you have to choose a suitably low frequency as the first carrier frequency, where balanced modulators are easy to build, and typical values that you would use for that purpose is about 200 kilohertz. In any case, it has to be much more than your bandwidth of the signal. Bandwidth is 15 kilohertz, so we are to choose a suitably larger value, right. So, this looks like a compromise, good compromise value. But then when you multiply your frequency by a factor of n to get this required modulation index of peak frequency deviation, this frequency would now become You are multiplying this with 3000, right? So it will become 600 megahertz, but that's not what you want, right? So this will imply FC2 is 600 megahertz, right? FC1 I selected on the basis of the first consideration is that it should be significantly larger than the highest frequency component in the modulating signal. Secondly, it should be small enough so that after frequency multiplication it is manageable, right? We are able to still handle these things. Also, it should be convenient to build a suitable balanced modulator at that frequency. These are the three considerations on the basis of which I will select FC1, right? So it will be a practical consideration, and this is a typical value that you might come up with. Okay. So how do we now take care of this? What's the answer? You have to have mixers in between. You have to have frequency translators in between. So you don't multiply the frequency by a factor of 3000. You do it in stages, right? And in between these stages, you can bring the frequency down to a suitable value, so that after remultiplication, you get the required carrier frequency as well, right? You do require a total multiplication factor of 3072, but that is realized in stages rather than in one go, and in between the stages you also carry out a frequency down translation, so that remultiplication would produce the corresponding and the required carrier frequency of interest. So that is the basic principle. So let us, yes please.
So how do you carry on mixing when the instantaneous frequencies are constant?
Okay, let me first complete the discussion and I will take up your question after that. So let me draw a diagram. So you start with a narrowband FM generator of the kind that we just discussed. Then you have a frequency multiplication, let us say by a factor of 64, and now I have a frequency converter here. You understand what is a frequency converter? It is the same, there are different terms which are used to represent mixing, frequency translation, frequency conversion, they all mean the same thing. And here I have to choose a suitable local oscillator, right, so that I get a value of the carrier frequency here after translation which is appropriate. So remember, your starting point is FC1 is 200 kilohertz, right, and delta F1 is 25 hertz. At this point your FC2 would be 64 times this, right, which is 12.8 megahertz, right, 64 times 200 kilohertz, and your delta F2 would be 64 times this 25 hertz, which is 1.6 kilohertz, right. Now by choosing a suitable local oscillator, let me give you some value, you will see why they have chosen this value in a few minutes. I will choose a local oscillator here of 10.9 megahertz, right. So what will happen to the signal here? Now this is important to understand. Your FC3 will obviously come down by, if you take the lower side difference frequency, rather than taking the sum frequency you are taking the difference frequency, right, that will become, so FC3 at this point would be 1.9 megahertz, right, and delta FC3 will remain the same. We are not doing anything here as far as when you do a frequency translation, all you are doing is whatever message signal you have, you are changing the center frequency of that, nothing else. So you will have an FM signal which is frequency translated to a different center frequency, that is all we are doing. So none of its properties regarding its frequency deviation are change, right? So your delta F3 remains 1.6 kilohertz. Now why did I choose this 10.98 megahertz? The reason was I have to frequency multiplication by factor of 48, Now you can see 48 into 1.9 megahertz will give you the frequency that I am looking for, right. So you get at this stage you get 91.2 megahertz, and of course you get your delta f4, which is approximately 76.8 kilohertz, right, which is actually 76.8 kilohertz, whereas we wanted 75 kilohertz, right. So that's your final FM signal. You power amplify it and transmit through an antenna. Okay, this is what you will transmit. So that's the principle of a commercial FM transmitter based on the indirect Armstrong method. Yes. Now let me take up the question that was being asked there. Has it been answered? Good. Okay. So I think if you are now asked to design an FM transmitter based on this principle, you will be able to work out the required factors. Yes, please.
Any other combination?
This is not a unique design, right? No design is ever unique, but practical considerations may require you to choose one over the other. Right? It may be convenient, for example, to have a crystal oscillator at this frequency from you, right? No design is ever unique. Keep that in mind. Any other questions? Okay, so we'll stop at this point and we'll discuss some direct methods for FM generation next time. Thank you very much.